Kyle, you're muted.
I'm not muted, you're muted.
I was
Hello,
muted.
everyone. Welcome to Scaling. I'll be your host, Kyle Coberly. So these are, I asked you what you wanted out of this. You told me the following. So a couple different angles that we can take on this. We can talk about scaling code. And we can talk about scaling users. Both of them are complexity after a fashion, but they're really two kind of independent topics. Let's start with the scaling code thing. So there's something I saw in your questions that I liked. One was, how do you go about choosing a design pattern with the future in mind? And like React may die, so how do we design around this? Okay, so the answer to this, to both questions, is actually super simple. You don't. I think most bad software is like got that way because you're trying to plan with too many things in the future in mind instead of dealing with what you have right now. One of the things that's kind of nice about code is easy to change. There's no concrete pylons. There's no land use permits. There's like very little stuff that keeps us from changing something down the road. And so with one like kind of small exception that I'll mention in a second, you don't want to design it for like if aliens come and take all the React code away and then you can't use it anymore, or loading up your project with a bunch of patterns designed around scalability or something like that. What you want instead are clean interfaces between different parts of the app. We call this decoupling. So it looks like if I have like the user part of my app, how users sign up, how we authenticate them, how we do all that kind of stuff. Maybe that's one block. And then we have the dogs part of the app. And then we have the reporting part of the app. And then we have the like database administration part of the app. So we want to make these pretty independent from each other and then have them talk to each other over messages. Can anybody think of something that like we've done already? We do all the time that kind of has this shape to it.
I mean, that's like an ERD, right? A relationship diagram?
Not quite. It's another diagram that we see all the time. Looks a lot like this. I thought I heard somebody for a sec.
I can't remember what it's specifically called, but like the HTTP requests back and forth.
Hey, there we go. That HTTP request thing. So when we were talking about the HTTP request thing, we were talking about APIs, right? So your front end makes a request to this API on the back end. Although all of us in here, we're grown-ups now. So it's time to learn the rest of what APIs are really all about. So what's the API acronym stand for? Anybody?
Application Programming Interface.
Thank you. So an application programming interface, we've used this term almost exclusively in the program to refer to a very specific kind of API called a web service. It's actually a very generic concept that we use all the damn time. The most important part of this is interface. How are you allowed to talk to me? What do I promise I'll give back to you if you talk to me in a certain way? If you send me an HTTP post request with this path and this body, I will create a new user in my database and give it back to you. That's an API. Also, I'm a function, and if you call me and give me a string, I will give you back that string in capital letters. That's also an API. I am a user service, and if you send me an object with these things in it, I will add that to the database. Not important to you how I do that, but that is the user service guarantee. Think about like somebody with like kind of a corny commercial. It's like that's the dog's guarantee. Is that if you give me these things, I'll do these things and give you this back. Those are APIs. They go all the way down to like function signatures. It's an API. All the way up to if I make this request over the web to this URL in this format, it does this thing. Also an API. Clean interfaces. How does this relate to scaling? I want you to think about this for a second. I'm going to call on somebody. What relationship does this have with scaling, do you think? Scaling code. I'm going to call on someone. Ms. Conjonabout, what you got? Well, how does it benefit us to be able to make something bigger, more complex, whatever, to have these clean interfaces here?
Well, how quickly your application runs and like how fast your application runs, how much memory it might take.
It's actually not that. This generally makes that worse even. And I still think it helps with allowing you to be more complex down the road. What else do you think, Tiffany? Why would we want to have all these things totally separate and just talk to each other via their APIs? The alternative is they're all just in one big bucket and they can talk to each other however they fucking want to because they all know about each other.
Is that the same idea of like with peer functions?
It is in fact the same idea as peer functions. Keep going.
The single responsibility principle? Is that?
That's kind of in the same family of what we're talking about. Keep going, you're making progress.
That way, if things change in your program, it will give you the same output either way, right?
Yeah! So if the dog service is talking to this user's service and we completely change how the user service is done, what does the dog service give a shit? As long as the API stays the same, this interface, it could go from being a flat file to being a Postgres database to being a Mongo database with an Express thing in front of it to a Laravel API. Who cares? If it has some clean like communication line, now nobody else really needs to worry about how this got done, only that the contract is being met. That's how you make a flexible architecture. Ask me some questions about that idea.
So is that like related? So what I'm getting out of this is if it's modular, if it's split into different pieces and there's a change or there's some sort of impact that happens to one of the pieces, because it's not in one big bucket, one big mess. It's you can change that piece, you can fix that piece, as opposed to having to redo everything. All you need to do is make sure the inputs and outputs are the same.
Yep. Worry about the interface. That interface stays the same. What happens inside this box, you can be fearless about changing it. If the users are really kind of entangled in the dogs and we're directly calling user management stuff in the reporting method and in the admin area, the dogs area, and all this other stuff, if everybody knows about how every other part of the app works, now one little change inside this box might break something over here, or break something over here, or break something over here. No bueno. We don't want to worry about changing code or deleting code or whatever. All we want to care about is these contracts, these interfaces. We uphold those. What happens after that? Kind of not the dog services business. Other questions about this idea?
Could you just say what a pure function is really quickly?
Sure. Pure function is given the same inputs, always generates the same outputs, doesn't have any side effects, and doesn't rely on indirect inputs, like a variable existing in scope or something like that.
Given inputs, outputs, no side effects. What was the third thing?
No indirect input.
No indirect input. Oh, thank you.
So, for example, there's a couple sneaky ones that'll catch up on you. So if I do something like sum and then return a plus b, pure function, like we don't have a hard time with that one, right? There's like one of the like subtlest ways you can make something impure though. Why is that no longer pure?
It's a side effect.
It has a side effect and something else.
It's another function.
No, we can use functions inside of other functions and keep them pure. This isn't one of those cases, but why?
It's doing multiple things, so it's not.
Nope. Something can be a gross 5 billion line function and still be pure. Good guess. Has a side effect. One other thing that it's also doing. Super sneaky.
Is it where it's returning a plus b, but it's also returning undefined because of the console log?
Nope.
Or no?
Good
Okay.
guess. Has to do with that. Where the hell did console come from?
Yeah, if console's not in scope, that function breaks.
Correct. So it's not pure anymore. It relies on console existing in scope and having a method named log. Indirect input. Now, if I also like pass that in, that can be pure. No side effects, no indirect input. Deterministic. That's the vocab word for same inputs give you the same output every time. So what would make something not deterministic?
Like using like random in the function.
Exactly. So if it has like a something like this. Whop, get a different output every time you run it now. Not deterministic anymore. What else might make something non-deterministic? Something we do all the time. Has a little bit to do with those APIs we were just talking about.
If you rely on anything that relies on like date time, like now, it's
Totally.
always going to spit out a different
Absolutely.
response.
That works the same way as math.rand.
Yeah.
So yeah, date, like date.now, anything that's using like kind of the internal date of the machine, that's not pure. What else though? It has to do with APIs.
Is it because you are reliant of the data of that API that makes it indirect?
It's somebody else's thing. They could return whatever they want. You don't know that they're going to return the same thing every time. That's not pure. And so it's a little bit of a tangent, but the pure isn't like, you can't do everything pure. It's not possible. You do have to have side effects. Like a program that doesn't have side effects doesn't run. Like the output of the program is a side effect. So if the program doesn't output anything, why the fuck did you write it? We want to be disciplined about how and when we do those things though. If your side effects are all at the end, if you're explicit about what your inputs are, if you're very clear about, like, so if you have like a network request you have to make, but you've separated out that request from what gets done with the request, if you try to find ways to keep the things that can be pure, works a lot better. And such.
So,
go ahead.
oh, I was going to say, so like something even like so whenever we make like a fetch helper, like parse HTTP response, like even though it's relying on the HTTP response, just that one line of response on JSON, that's a pure function.
Correct. Given the same thing, you're going to get the same output anytime. The response was explicitly passed in. And we're not going to talk about types in this, but like we could guarantee that the type says that it has a .json method. So yeah, the impure part of that is split out from the pure part of that.
And so does that help with like, so the way that I'm thinking about this is if I've got a, like a 10, 15 line function that doesn't do a whole lot, but there are some variable elements in it. And if you can split it out into as many pure functions as possible, when there's a problem, this is where it broke right here, because that's the thing that changes.
Now, like there's some gotchas on that too. So for example, no, that's sum function. It's easy, man. So I've got my sum function, takes in a plus b, and I just return a plus b. All right, it's a pure function, man. I know exactly how that works. And so then I sum 0.1 and 0.1. Oops, nope, 0.1 and there we go. 0.1 and 0.2. Oops. The problem was right there in the pure function. But the floating point math broke. So you still have to consider like kind of weird edge cases and stuff. Purity doesn't mean that the logic does exactly what you think it does, but it helps. Other questions about this idea of having decoupled code? Here's another cool thing. All 4 of these little services here, that could all be part of one project. They're different JavaScript modules, they're different Ruby classes, they're whatever else. They could also be over a network. They could be like APIs, like the web services that we've been using. Why not? If you've decoupled that interface, maybe this dog service is written in Rails. Maybe this user service is written in Express. Who cares? They're just talking over HTTP. They don't know how each other are implemented. Or maybe all of this is part of a Rails API, and that's a dogs class and a users class and a reporting class and an admin class. Get a lot of flexibility there. Now, the patterns that you use within those, back to the original thing, how do we choose a design pattern with the future in mind? Don't. You want to be ruthless about being able to change anything inside of one of these boxes. And you want to be real careful when you're setting up these APIs, because that's a contract. Anything that depends on that contract, you change the contract, you're going to have to change all of those. Oh, not so good. Everything inside of a black box, though, fuck it, be ruthless. Other questions about scale and code? All right, let's check for understanding. So I would like each and every one of you to write me, let's call it like a paragraph, two, three, 4 sentences. Send me a Slack DM with what you want to keep in mind when you are trying to code with the future in mind, code with scalability in mind within a project. Let's take 3 minutes on that. Go. All right, back together now. So, Kat, I loved your answer. Would you please read it out loud?
Sure. So in order to code with scalability in mind for a project, it's important to decouple your services. This way, it's easier to update and change one piece of a project without breaking everything or having to overhaul the entire project. As long as you can keep your APIs the same between services, they will continue to interact and act as expected.
Beautiful. Couldn't have said it better myself. And so like in practice, this is a good example. So I had a client recently that is switching from like a PHP monolith to like Vue components. So they were rendering everything kind of like ERB style, but with PHP. And they want to start using Vue components. And so what I encouraged them to do was find those services in there, move those services over to this, and try to keep those isolated so that we don't have to rewrite the app. You rewrite a service so that it uses, you know, whatever kind of approach or language or framework or architecture you want, and you have it decoupled from everything else. Cool. Other questions about scaling code? Yeah, Kat, I think you got a fan club. Go ahead and paste that in chat.
As like practically, is this like another way? Hang on, doesn't matter. I don't know why I'm asking. Never mind.
Go ahead.
No, so I was just thinking, like, is this another, so we think of like thin vertical slices as like a way to just like manage our workload, but is it also a way to be like, to keep track of stuff like this? Like if you're just focusing on like one specific thing, then you can not fuck everything else up.
So yeah, if you have your thin vertical slices, so like a thin vertical slice is supposed to be a complete feature. It's all the way done, right? So if your thin vertical slice is also independent of all of your other thin vertical slices, and they just communicate with each other through messages, now you're getting this scalability. I'll give you one more example of what this kind of looks like in practice. So this is from a talk I gave years ago. Let's see, Vue. There we go. App architecture with Vue. So this is generally the architecture that I recommend in Vue apps, and it's designed with this kind of idea in mind. You're separating out how data gets used in the app, that's these orange boxes here, from how the data is stored, which is these green boxes, and how it's retrieved, which is these blue boxes. If you keep those things independent from each other, if you're doing this locally with just some data from a JSON file on your computer, cool. Nothing in orange or blue down here has to change to accommodate that. This doesn't know where its data came from. All it knows is it got it from the store. The store is communicating with a fake API instead of a real API. How would it know? All it knows is the model and the adapter said that I got my thing back. Cool. So then the adapter is the only thing that knows whether or not the request was real or not. Figure out what you can make not something's business. How the data is retrieved, how it's used, those are two separate concerns. Split them up. Cool. All right, let's talk about the other kind of scaling. So scaling like users, or really I guess scaling use. two different kinds. One is vertical scaling. The one is horizontal scaling. So both of these have some different implications to them. Vertical scaling is more out of one machine. So if we can take like one server or something like that and get it to do more, perhaps because our code is more efficient, or we're using a language or a framework that like doesn't take as much resources or something. So we got vertical scaling there. Horizontal scaling is add more machines. So if you have a server that can handle 100 users and you need to handle 100 more users, just add another machine. Need another 100 users? Add another machine.
Is that the same concept as like having a very powerful, very expensive like mainframe computer versus spinning up a bunch of virtual machines to run off of?
Yep. Or like horizontal scaling is what supercomputers do.
By just spinning off different instances? Cool.
So there's some implications to these. So horizontal scaling implies that it can be horizontally scaled. Let's take a look at how that might work. So you're the user, you're using Facebook, you're using some huge site. So you have your HTTP request come in. Where do you think it goes? Surely 2 billion people aren't hitting the same computer.
So like the first available.
How does it know? All I did was type in a URL.
I would say each little component has logic to send different requests to different places to get what they need.
Okay, any other guesses?
And I'm guessing on the back end, there's a dispatch service that sends those requests
Yeah,
specifically where they
something
go.
like that. I like that word, dispatcher. So you've got like a dispatcher, traffic cop, someone like this. And this thing's job is to know who's busy, know who's available, know who's broken. So if we have all of these servers over here, it can figure out which one is capable of handling the request. Need to handle more traffic? Add another box. Tell the dispatcher we've got another one available. One of these breaks, dispatcher finds out about it. We got a failed request. Take this one out of rotation until we figure out what's going on.
What does the dispatcher look like?
So
I mean, like this, but
so like in practice, it's probably a load balancer. So I've seen the physical machines that do it. Like, let's see, server F5s, I think they're called. I think these things that make the actual like some of the like actual machines that do some of this. There we go. load balancing. Well, probably what most people use anymore is Elastic Load Balancer, which is an Amazon service. So request comes into the load balancer on AWS. Load balancer's job is to make sure that the load is balanced across the machines that you have, and so on.
Does it get to the point where you would need to have more of those? Like, do those get overloaded too?
There's only so much like one machine can take, but hey, we're back to this APIs idea. That shouldn't be our business. We want, say, hey, if I send a request to this IP address, it figures out what happens after that.
Isn't there a way in, I know you can do it in just like raw SQL, but that you can striate your data based on how often you think that requests are going to come through for different pieces of it. So like, for instance, if you have timestamp data, then like maybe everything in the past year is more readily available. It's like split off on a certain, I can't remember what it's called.
Indexing, but we're not even there yet. We're still just talking about processing. Data storage is the next thing we're going to talk about. Okay, so I mentioned there's an implication here that this stuff can be split up. Bunch of web requests, easy. That's what this kind of stuff's made for. What if it's one great big request? Like scientific computing, trying to predict weather patterns and stuff. Maybe you're going to need a bigger machine. Or anybody know how well we can combine those two ideas? Happens all the time in scientific computing, big data.
Multi-threading.
Kinda. This is like super duper multi-threading. If you can split up the problem into smaller pieces and then have each one of these work on a smaller piece of it and then combine the result, that's called map reduce. You map over the smaller pieces of the problem and then you reduce a solution together. So it's just like if you were doing that with like a function chain or something, except you're doing it across a network with different computers. Okay, one other big problem with horizontal scaling. And it has to do with what Jack said. It has to do with data and databases and stuff. Anybody know what it is?
It's not incredibly efficient if you've got like a bunch of servers that are like okay, but they're not as elite as something that would be more vertical scaling.
Maybe. Think about the data.
If you've got a large data set and you're working with a bunch of like low powered machines or low powered requests, it's going to take longer to query the data set than if you've got like a bigger computer.
Maybe. Machine. But keep in mind too that one of the reasons we split all this stuff up is that it can get us the stuff faster than one super big computer that's too busy.
Would you have to worry more about keeping those pieces in like order and like sorting it and not getting a jumbled mess back?
Ooh, we're starting to get a little bit closer. We're like 30% of the way to what the problem with this is. Okay, what if I add another 100 green boxes to this? 1,000 green boxes, billion green boxes. Those are all servers. What about this?
Oh, you're still hitting. I mean, you're still hitting the same endpoint. They're all reaching the database. So that's where you're glad now you've got a choke point there instead of on the machines themselves, on the servers themselves.
Correct. Now, like, there's no magic here. This is still just a fucking computer. All right. So if it's just a computer, that's got limits. So got a couple options. There are database solutions. So like this is way past like what we do with databases in the program. But there are databases that are designed to exist across networks. So we can get some horizontal scaling with databases that way. We add more nodes to the database. You still have the problem of like a single point of failure too. That database gets corrupted, your app's gone. Oops. So maybe you have a couple different databases. What's the issue with that?
Redundancy?
Yep. How's that an issue?
So it'll be more expensive for one thing, because you have to hold all of the data in complete stores in different places. That's not the main problem, though. It's
And like, what's your source of truth?
oh
Yeah.
Databases.
This says I have Bixby. This says I have Bixby and Mesa. This says I don't have either. Because even if these like eventually get synchronized or something like that, they still happen in time. They can't literally happen simultaneously.
that doesn't seem like it's as if you sync as a single source of truth on like a regular basis, depending on the type of data you have, it doesn't seem like the end of the world, right? Like if I'm fucking like Google, for instance, right? Like I don't give a shit if what your search results on the Eastern Seaboard match the Western Seaboard in a single moment in time, but maybe by the end of the day have it link up.
Yeah, I guess it depends on what is frequently. Is it synchronized every second, every day, every month, every year? And then like, so if we have a little robot that who kind of runs around back here, just, okay, well, there's something over here. I guess I'm going to copy it over here and copy it over here. And this is running back and forth and doing those things. That works. And yeah, some stuff doesn't matter. If I make two different requests to the database and I get different answers back, this is one of the reasons that people use like local storage and cookies and some of those kinds of things. Because then it's faster because you're just working with local data and you're reducing the likelihood that you're going to get two different responses back for the same question. And then eventually they get synchronized. So cool, we got that going for us. But this kind of comes back to this idea. What needs to be spot on? Stock prices? Well, that stuff to be legit. So what stuff does it not super matter if it agrees at any one point, and as long as it eventually agrees? What stuff needs to be perfect? Can you split those things up and have them communicate with interfaces?
Isn't what is it? Eventual consistency is one of the main properties of something.
Cap theorem.
Cap theorem.
I'm really regretting writing these vertically. Consistency, availability. partition tolerance. All right, so CAP theorem is that you can either have consistent data, meaning that it's exactly the same across the board. You can have available data, meaning that it's always available. And you can have partition tolerance, meaning that it can exist in more than one place. You can have any two of these, but never all three. That's CAP theorem. And so since we're talking about web stuff, partition tolerance is a given. We're accessing stuff over networks, that's a partition. So that means that this is a given. So we can either have our data be consistent or always available. If it's always available, well, stuff occurs in time. And so any two different parts of the partition might have different data. Or we can take the system down while we're making everything consistent, and then everything agrees. But we have to pick between one of those two things. So if every time this robot is synchronizing something, the system is unavailable, then we chose consistency. If we're okay with it being eventually consistent, then we choose availability.
Do either of those have a best practice, or it's just circumstantial?
They are truths to be aware of when you're designing solutions. So like I learned about CAP theorem from a guy named Mike Pack, who's a local hero. And he was doing an app for like medical data in Africa. And one of the things he found is that like the power in clinics and hospitals and stuff in Africa is terrible, goes out all the time. And so like eventual consistency is kind of what you need because it's already not available. So like you really need to, so like you lean more on the C side of that. It's just it's a thing you have to be aware of. It's a hidden constraint in designing these kinds of systems.
You also split your database across these instead of having like 3 duplicate databases. You can
Correct.
split a relational database. You can
Yep.
query each table that way.
And then what you're in effect doing now you've got a service. This is our user service. This is our dog service. This is our admin service. And all right, well, so those things that are communicate with it directly, they can go through some kind of another dispatcher, traffic cop.
Stored procedure.
Sure.
I'm learning about now.
Wait, is that what microservices are considered?
Yep. So microservices is this if they're all deployed separately. And we don't know what language or stack or anything. And one of the cool things about microservices is if we're already doing that as just kind of an architecture practice anyway, and we can deploy all these things separately, now we can scale them separately too. So if your dog service sees crazy traffic, we can have all kinds of servers behind this. The reporting service only gets used every once in a while. You don't have to scale it so much. If you have, for example, a Rails monolith, if you're scaling it, you're scaling the entire thing. And then like the pinnacle of that is AWS Lambdas. So like a Lambda is a function as a service. You write a function in whatever language, and it can connect to a database, it can do whatever else. And then you send an API request, hits the Lambda, runs the function, gives you the response or whatever, and then it turns off. And you pay a fraction of a penny every time that function runs. So like your scaling costs are very narrowly like coupled to how your app is used. And that's the dream. You don't want any excess capacity that you're paying for, but doesn't actually make your app any faster. Lambdas are like perfectly tailored for how your code actually executes. That's what's fucking cool about it.
How is Lambdas related to microservices?
It's a common way to run them.
Got it.
So
Okay.
you make a microservice and then you would run it on a Lambda. And then, okay, so here's another consideration with all this cool scaling that we've been doing. All right, so we make an HTTP request over here to a dispatcher. Dispatcher figures out which one of these servers is up. So it makes an HTTP request also. And then we need to get something from a database. So we go to our little database dispatcher. That's another HTTP request over there. And then this thing is figuring out that we need to make an HTTP request over here. And then this is making some other kind of protocol request to this thing, which might be on a different computer. So I wanted to get Pikachu, and I ended up making 1, 2, 3, 4, 5 network requests behind the scene to do that. What's the problem?
Network speed.
Network speed. What does Old Man Coberly always say the slowest part of your app is?
Got to send shit to space.
Yeah, man. That's happening every time. It's happening 5 times every time you make a request. How on earth does Facebook manage such a thing? So network requests are slow as hell. It's not necessarily the protocol, it's the go into space part. It's that if my computer here in Colorado has to make a request to this dispatcher, which is in Oregon, and then that dispatcher makes a request to a service in North Carolina, you're up against physics at some point. We're like, there's a universal speed limit, man. Only so fast we can do this stuff. So here's the catch. With modern cloud technologies, every one of these things can exist in the same VPC, virtual private cloud. The physical machines for all of these things are in the same data center that Amazon has in Oregon or wherever. They're all physically co-located. They might even be on the same physical computer. But you get to use these abstractions so that when you're making these requests between these, it's not going to space and back. It's going to like somewhere else on the hard drive. Or at worst, to the other side of the room. But we get to treat it like we've got these decoupled things where we're just making interface requests. So how do you scale that? Well, you make it Amazon's problem. They look like that. They are huge. There we go. There's a big one. It's the scene from Silicon Valley, and your box would go here. So some like this computer over in this corner making a request to the thing in the other corner, that's still pretty fast.
Where do those things like live? Like, where does Amazon have its data centers? Is it just like all over?
So let's see if I log in.
Wherever they can get the cheapest power, usually.
You are correct. And
They also split them geographically too, though, right? Just to like because of the wires, right? Like you'll be like the Eastern Seaboard. If you're like in New York, you know, you want to access it from there, not from like California.
correct. There you go. There's where Amazon's data centers are.
So if say one goes down, there's like something that destroys it. What happens is that data lost? Do they have like, they probably have backup situations to like move it to something else, right? Hopefully.
Who knows? It's whatever your service level agreement with them is. In practice, yeah, probably. Also, like, these go down all the time. Like, most recent one I can think of was a couple months ago. USC's 2 went down. And so did like a third of the internet. So like, yeah, these things absolutely happen. Oh shit, you know what it was? Remember when nobody could get on Slack and we had to like do all that shit over email? USC's 2 went down. So that's what happened. Yeah, somebody like bombed it. I don't know. That's inside the black box, man.
It's kind of concerning.
Could be, but like, consider this too. I know I've talked with engineers who, for that reason, will go, I don't know where that server is. They say it's in USC's 2. They say it's in Ohio. It could be in North Korea for all you fucking know. That's why I put mine in my basement where nothing bad could ever happen. So like, there's also risks to doing all of this yourself. And for example, that same company that wouldn't use cloud services because, well, what happens if something breaks? Their backups for all their customer data were also stored in a second folder on the same computer marked backup in the basement of a building that floods all the time.
Oh my God.
So like, you're kind of trusting, can Amazon manage that problem better than I can? And the answer is almost definitely yes.
That's the argument about like.
Sydney, finish your thought.
Oh, sorry, Sydney.
I just said that's true. No, you're totally good.
All right, Jack, what's on your mind?
That's the argument about like public cloud versus private cloud versus community cloud, right? And like these like with these VPCs this is like a community cloud, right? Because like they're being distributed between multiple machines, but they're also located in the same place as like fucking Dropbox's data or whatever. I guess that's a bad example, but because you're using the same community space, but it's bouncing it back and forth. It's not like a localized thing.
Correct. Awesome. That's scaling. What else you want to know about it?
It seems like in our position as starting developers, and if like we're working on our own personal projects, there's not really a good way to get around using like Microsoft Azure or AWS as kind of like a service management program. What is that right, or what would you say to that?
No, that's true. Even like Heroku is a really cool interface on top of AWS. It's still AWS.
Right.
Yeah, AWS, GCP, Azure. Actually, I just was looking at this yesterday. So I was in a fight with somebody about AWS's market share. Let's see, AWS market share. They're not the only people who do this, but we go down to the charts. There you go. Mostly AWS, a little bit of Azure, barely any Google Cloud. Alibaba is the Chinese competitor to AWS. And then all the others like OpenShift, a couple others like that, make up the rest. But this stuff is commodities. Servers, databases, and stuff. There aren't like handcrafted nice ones. Like it's electricity. So like it makes a lot of sense to just outsource all of that. There's no reason that anyone in your company should be buying computers and like racking them up and networking them together, any of that shit. Waste of time.
Is this are there is there a striation between the types of companies, the types of services that you run on the cloud-based platforms versus like one cloud-based platform versus another? Like, for instance, we're all on Macs, but Windows owns the just runs the gamut of the operating systems market, right? So like if we're I'm trying to think of a good way to put this. Like if you're running like a really data intensive application or like an analytics intensive application, would you be better to use like AWS versus Azure, or are they both just so massive that it doesn't matter?
Like, what other deal do you have with Microsoft that might make Azure a lot more competitive? This is like market-based pricing stuff too. And so like, I don't know, maybe Azure's super cheap now, or maybe some particular Azure service is cheap. Or like another thing that happens with AWS is you can buy like overflow capacity they have for radically reduced amounts, but you might have downtime as it's switching over. And that stuff fluctuates like day to day. Like what other services do they have that you might want to take advantage of? So like one of the reasons that AWS has so much market share is they have a billion fucking services. Anything you could imagine they probably have in there. Whereas like GCP, like less so. And they're always playing catch up too. Like AWS leads this. And so like when AWS came with Lambdas, totally game changing. Google's version of that, which is like Google Cloud Functions, it took them a year to make their version of that. So like you've got some of that going on. Also, you might not need some of the like wackier stuff that Amazon has, but you want better Watson integrations. Like IBM has some of this stuff also. And they also have Watson, which is the like best AI processing available right now. So like all of those things factor in. What other deals do you have? What services does like your product need? What are current prices? Also, like AWS is a nightmare to use. I use it, but it is real rough. The documentation is terrible. It's so hard to do anything correctly. It's a lot easier to do that stuff on GCP. It's one of the reasons they're like a job that at least one of you will probably get is like Amazon solutions architect. Your job is just to understand how to use their billion fucking services because nobody else can figure it out.
This was like a fight in code opinions yesterday, wasn't it? 2 days ago, something like that.
That's what I was referring to. Yep.
Okay.
Yeah, code opinions. We're going back and forth on this because, and I really liked this. The people who made AWS were saying that we were trying to figure out ways to improve communication until we realized that communication was the problem. We don't need to make it more efficient. We need to make it go away so that nobody has to talk to each other anymore. And so they're like, well, what if all these different like teams and projects and stuff didn't have to have cross-functional status update meetings? Instead, they just had interfaces. They had APIs they interacted with each other over. And like, that was the magic. That's how AWS is able to move as quickly as it does. The trade-off is that every service is a little bit different. The documentation is way fragmented. There's plenty of other problems that go along with that, but nobody's going to catch up to them unless they're also doing that strategy. You just move too fast.
Have you used Azure?
I have not.
The interface is cool. I was just wondering because I only used AWS a little bit, but Azure we used for I think it was for like setting up auth or something like that. And the interface is pretty clean.
Yeah, like that's the easiest way to win against AWS is like, hey, look how not shitty this is to use. But then like one of the trade-offs there is that AWS's GUI interface is awful. Their command line interface is baller. And so if you like live and die on AWS, you probably spend a lot more time on the command line than you do their garbage visual interface. Cool. Other scaling questions? Heirloom servers. Small batch. Cool. See y'all stand down.